Thank you very much. I'm Hiroya Nakao from Institute of Science, Tokyo. It's my pleasure to be here. Thank you very much for the organizers. And I'm classified into control, but actually I'm not talking about control. I'd like to talk about Koopman operator approach to limit cycles in quantum dissipative systems. And I have 20 minutes, right? Okay, I am basically a physicist and studying nonlinear phenomena using nonlinear dynamics, stochastic processes, and etc. And today I'm focusing on these open quantum systems. But before going to the open quantum systems, let me start from the limit cycles. So okay, so there are many nonlinear oscillations in the real world, and we are interested in it. And if you have rhythms, they typically synchronize. So how to analyze synchronization is important, and synchronization can have many functional meaning in animals, or maybe also in robots or whatever. Okay, and I'm interested in how to analyze them for a long time, and these systems are very complicated, high-dimensional, nonlinear, but as the statistical physics tells us that in dissipative systems where energy dissipates, the state is often attracted to a low-dimensional manifold in the state space. And if we can find the key variables characterizing such low-dimensional manifold and find the equation of motion for such key variables, and they give us much more insights than just considering the original high-dimensional nonlinear Hamiltonian. Okay, and from the limit cycles community, the so-called phase reduction has been a very typical example of such method, and I'm very familiar with it. And then, as you know very well, Igor and many collaborators, Alex, introduced the Koopman operator viewpoint and in this field, and okay, and they actually give us more ideas and generalizations. Okay, and this lower figure shows us, for example, you have a fluid flow, which is oscillating, and it's of course a very high-dimensional dynamical system, nonlinear. But if we are interested in only in the oscillations, we can introduce phase, and we can actually reduce the Navier-Stokes equation, which is very high-dimensional, to a single phase equation, at least for small perturbations. And this can actually be done, as I did with Sam Tyler several years ago. Okay, and I think, okay, so this is just operator and generator I can just safely skip. We are mostly interested in the generator of the Koopman operator, A, which I use A, okay. And, okay, so this, okay, and as you know very well, there are, so for linearly exponentially stable fixed points, the limit cycles are maybe toruses. We have the so-called principal Koopman eigenvalues, and they are just the stability exponents of the fixed points, or the limit cycle Flock exponents for the limit cycles. And we have the associated Koopman eigenfunctions. And if we introduce a new variable y using these Koopman eigenfunctions, so we can linearize the system like this. So this is great. And moreover, okay, for stable attractors, these lambdas are negative. So we can eliminate the very negative ones to get a reduced order dynamical system. And if there is some additional perturbations, if it is sufficiently weak, we can still do the same coordinate transformation using the Koopman eigenfunctions and get an equation like this. So it's a linear here plus some sensitivity function, and then you input. And this Z function appears actually in the traditional phase reduction theory for oscillators, and it is called sensitivity function. And this is a kind of generalization. And if we eliminate some of the variables, we get lower reduced order linear simple equation, which is much easier than the original system to analyze. Okay. And okay, for limit cycles, okay, so we have the frequency and the Flock exponent, omega and mu like this. And the Koopman operator has, so, okay, so these are the principal Koopman eigenvalues, and we can introduce the associated Koopman eigenfunctions, and they are like these. Okay, so we focus on, sorry. Okay, these two frequency eigenvalue, and in this case, we have just a single Flock exponent associated with amplitude, and we introduce two eigenfunctions. Then, as I showed before, okay, so this is a phase amplitude reduction of limit cycles originally formulated in geometrical manner from the operator theoretic viewpoint, according to Igor. And so by using two principal Koopman functions, we can introduce a phase, which is actually an argument of the first one, and then the amplitude in 2D case, and then reduce the equations like this. So we can get the phase equation and amplitude equation by using those principal eigenfunctions. So, and this Z function has long been called phase sensitivity or phase response function. And this I function was recently introduced by Igor, Alex, and called isostable sensitivity function. I would call it amplitude sensitivity function, because otherwise I have to call Z the isochron sensitivity function. That's a bit unusual in my field. Okay, so this is a famous picture by Alex. And okay, so we are basically simplifying the system into a linear one, which are easier to analyze. Okay. Now we go into the quantum systems. So, okay, we can consider more and more smaller oscillators, and they actually done in many fields of science and engineering. So eventually we have to go into quantum systems, quantum regimes, and there the system is described not by an ordinary differential equation, but by an equation for the density operator. And I'm glad that Professor Giannakis gave a good introduction to this. So we have this law is called density operator or density matrix, which can be infinite dimensional. And okay, they satisfy these quantity equations, and they obey the so-called quantum master equation. Okay, and this is a commutator, and this H is Hamiltonian, and this D is called Lindbladian in this open quantum systems field. So that describes the interaction of the system and the environment through some operator L. So here we have n such reservoirs, environments, and through this Lj, the system is coupled to those environments. It's like this. So this is a cavity, and we consider the field there, electromagnetic field in the cavity, and this electromagnetic field is given by this law. And its interaction with the outer world is described by this D of L. So this is an open quantum system. It has a long history in physics. And okay, then we can also introduce different representation of the law. Law itself is a bit abstract and difficult to interpret. There are methods, so-called phase space quasi probability distributions, to represent law in a more understandable manner. And so we can introduce some ordinary function, not an operator, P of alpha, or the so-called Wigner function, which is given by W of alpha, like this. Okay, and here alpha is the coherent state of the system, which is an eigenstate of the annihilation operator. And annihilation operator is an Dirac. So if you don't know, I think I cannot explain in a short time. So it's used to very fundamental tool to describe Hamiltonian harmonic oscillators in quantum physics, very fundamental. Okay, and this coherent state is localized state. If mapped to this Wigner distribution, it is localized in the space, position, momentum space. It's like a Gaussian packet in this phase space. So it's quite useful to see, project the law into this to see what's happening in the system. And very commonly used in physics. Okay, now then there are models of quantum limit cycle oscillators. And I think this is the one invented for the first time. And okay, so this is the quantum master equation. And this is the Hamiltonian part. And here we just have A dagger A. And this is just a Hamiltonian for a harmonic oscillator. So it's not a limit cycle oscillator. Then we have two environmental couplings. The one is a negative damping with a reservoir, and the second one is a nonlinear damping, second order nonlinear damping. And okay, so this excites the system, so increases energy, while this nonlinear damping suppresses energy. And if you know van der Pol, and this is exactly the negative damping and nonlinear damping, so this is called quantum van der Pol oscillator in this paper. And if we simulate this quantum master equation, we get, okay, so this is a Wigner distribution projected on the XP space. And along the classical limit cycle, okay, so this is a semi-classical situation. Along the semi-classical limit cycle, we have this distribution of the Wigner function. And this is for a stronger quantum regime. So and this correspondence, semi-classical comparison with the semi-classical becomes different now. And I think this is not realized yet, but possible real world system can be ion traps or lasers or maybe something else, okay? And we want to do the phase reduction based on Koopman operator for this system. And actually, in the semi-classical regime, we can definitely do it because quantum systems can be approximated by classical stochastic process. So, and that can be done like this. So suppose we have a quantum master equation with a limit cycle, then we go to the P representation by the quasi-probability distribution, and typically we get this type of infinitely many partial differential equations with many terms. But if there is some small parameter which represents how quantum it is. And by truncating this expansion at the second order, we get an ordinary Fokker-Planck equation. Then we can go back to the stochastic differential equation corresponding to the Fokker-Planck equation, and we can get the so-called semi-classical dynamics for quantum system. So it's like this. So we start from the density operator, we go to the Wigner distribution, then, okay, we are interested in this individual trajectory that can be limit cycle plus some noise, and this noise approximates the quantum effect in this system. Okay, now, then, because we have now classic trajectory approximating the quantum trajectory, we can do the phase reduction. So now we have some additional perturbation to the system. Then we do the same semi-classical approximation. And if this f of x, which has a stable limit cycle, we can do the phase reduction or phase amplitude reduction, as I said before. And we get, now because we have a noisy phase model described by phase stochastic differential equation. Okay. And I think I have some time more. Okay. Okay. So this is one of the main results. So we can do phase reduction for quantum nonlinear oscillators in the semi-classical regime. And okay, this is an example. So this is the quantum van der Pol oscillator with we add some periodic driving, like electromagnetic field. So, and we want to synchronize this quantum van der Pol oscillator. And this is a Wigner distribution under the influence of periodic driving. And eventually, this becomes a cyclostationary state representing the synchronized state of the quantum system to the EM field. And this situation can be represented by this equation, phase equation, approximately. And here, so this is original quantum master equation simulation. And this is just a result of the phase equation and then reconstructed the original state. And you see they are mostly okay at this level of quantum effects. Okay, and I think I have. Okay, so this is the end of the second part. Then now I go into the last part. Okay, so we could successfully get the phase equation for the semi-classical nonlinear oscillations. But then, of course, this is just semi-classical approximation. And in reality, the interesting quantum phenomena occur only in strongly quantum regimes, like entanglement or coherence. And so we have to go into deeper quantum regime. But then we cannot truncate this equation at the second order. So we cannot get the quantum Fokker-Planck equation, and we cannot get the stochastic differential equation, and we cannot do the classical phase reduction. So we have to consider the system from free quantum in a free quantum mechanical manner. Okay, so we have to. Okay, now the Koopman comes back. So okay, so this is a quantum master equation, and which is a kind of Schrödinger picture. So we consider the system state evolves, while the observers are stationary. And I didn't say, but as a professor show in a very concise manner. So in quantum, expectation value of some observable f is given by this formula according to von Neumann. And if we introduce a trace inner product like this, then it's given by this. Okay. Then we can introduce the adjoint operator with respect to this trace inner product of this. Okay, sorry, this L is called Liouville super operator because it acts on an operator law. And we can introduce the adjoint of this L, adjoint Liouville operator, and it can be calculated to be like this. And if we use this operator L star, then now we can go to the Heisenberg picture. So we fix the system state, but evolve the observables. And it evolves with this linear equation, very familiar to us. So this L star is a Koopman operator in this system. Then, as I said before, the phase is a Koopmanian function associated with I omega, and the amplitude is a Koopmanian function associated with mu. So we attempted to introduce the phase and amplitude, and okay, here only for phase, using this I omega. Now we have dissipation, so it's slightly negative positive part, but maybe we can still define phase using these eigenvalues. Okay. And this is a semi-classical case, and this is a strong quantum case. And okay, so this is a result. So in the semi-classical regime, if we define the phase by this, we get something very close to the semi-classical situation. So they are very similar. While if we do in a strong quantum regime, they are really different. Okay. So in the strong quantum regime, we should definitely use a phase for defined in a free quantum manner. Okay. And okay, this I think this is unpublished data by Yuzuru Kato. He also did this amplitudes. And in the semi-classical regime, they are very close to the classical limit, while in the strong quantum regime, they are different. So these are the spectrums of the adjoint Liouville operator. And okay, so and this is still ongoing, I think. Okay, so to summarize, okay, I'm interested in these mixed systems, and phase reduction has been a very common method to analyze it. And the recent development in the Koopman operator theory provide an operator theoretic rather than geometrical approach to phase and reformulation to the phase amplitude reduction. And it seems we can also extend the theory to quantum systems. And in the semi-classical situation, it works nicely. But in the free quantum regime like this, we could calculate these functions, but we have no idea of how to use these functions because now we cannot reduce the dimensionality so easily. So I'm still wondering how to use these quantities in free quantum regime. Okay, that's all. Thank you very much for your kind attention.